In lesson 13.6, you will apply the law of cosines. We're going to solve triangle ABC. So I'm going to draw triangle ABC. It's an oblique triangle. And I'm going to label the parts that are given. So side C measures 19, side A measures 22, and angle B is an 81-degree angle. So this triangle is side angle side, which cannot be solved by the law of sines because we don't know an angle and the side opposite it. So we're going to have to use the law of cosines to help us find angle A, angle C, and side B. Now using the law of cosines, we're going to have to find side B first because we know the angle opposite it. So B squared is equal to the sum of the other two legs squared minus 2 times the product of those legs times the cosine of the included angle, that 81-degree angle. And now to get just B, we'll have to take the square root of both sides and use the positive value that we get when we take the square root of both sides. So in our calculator, we're going to put the square root of 19 squared plus 22 squared minus 2 times 19 times 22 times the cosine of 81. Make sure your calculator is in degree mode. And I'm getting 26.72 for side B. Okay, and now because we know an angle and the side opposite it, we tend to use the law of sines to find the next measure. And I'm going to find angle A. So sine of A is to side A, which is 22, as the sine of angle B, which is an 81-degree angle, is to side B, which we just found to be 26.72 units. So solving for angle A, we know that we're going to multiply both sides by 22, and then to get just an angle we need an inverse function. So angle A is equal to the inverse sine of this ratio, 22 times the sine of 81 degrees divided by 26.72. So use your calculator, put that in our calculator. So I've got inverse sine of 22 times the sine of 81 degrees divided by 26.72. So I'm getting a 54.4 degree angle for angle A. 54.4 degrees. Okay, and now that I need angle C and I know the other two angles, now I can just subtract. So angle C is going to equal 180. Take away that 81 degree angle and take away that 54.4 degree angle. So I'll run that through my calculator again. And I'll get a 44.6 degree angle for angle C. Okay, and now a quick check of proportion. Again, remember the smallest angle, which is angle C, is opposite the shortest side, and 19 is the shortest side. And the largest angle, which is angle B, is opposite the longest side, and 26.72 is the longest side. So everything's in proportion. This triangle is solved. Okay, let's solve another triangle. Another oblique triangle, which means it's not right. And this triangle happens to be a side-side-side case, where side A is 8, side B is 12, and side C measures 10 units. So what we need to find are all three angles, all three angle measures. And since we don't know a side and the angle opposite it, we have to use the law of cosines. So I'll start by finding angle A. That means the side opposite it squared is equal to the sum of the other two legs squared minus 2 times the product of those two legs times the cosine of that included angle, angle A. So we need to get the cosine of angle A alone. So we'd subtract 10 squared from both sides and 12 squared from both sides, and we'd divide both sides by that negative 2 times 10 times 12. Okay, and to solve for just A, we need an inverse function, inverse cosine of this ratio. So that's what I'll put in my calculator to solve for angle A. Inverse cosine, and in the numerator I have 8 squared minus 10 squared minus 12 squared divided by a denominator of negative 2 times 10 times 12. So I'm getting a 41.4 degree measure for angle A. Okay, and now angle B, now that I know a side and the angle opposite it, I can use the law of sines. So the sine of B is to side B, which is 12, as the sine of angle A, which is a 41.4 degree angle, is to side A, which measures 8. So again, sine B is equal to 12 times the sine of 41.4 degrees divided by 8, and solving for B, we need that inverse sine function of 12 times the sine of 41.4 degrees divided by 8. So I'll enter that in my calculator to approximate angle B. Inverse sine of 12 times the sine of 41.4 divided by 8 is giving me 82.7 degrees for angle B. And now, because I just have one angle left and I know the other two, I can subtract. So C is going to equal 180, take away 41.4, and subtract 82.7. So in my calculator, I get 55.9. degrees. So we found all three angles, and this triangle is solved. Okay, in the second problem on this page, it says in Junior League Baseball, the pitcher's mound is 40 feet from home plate and the bases are 55 feet apart on the square field. How far is the mound from first base? So let's draw this field. Okay, with it's a square field, square, with 90-degree corners, and the problem tells us that the mound, the pitcher's mound, is 40 feet from home plate. That distance, that line, divides this right angle into two equal pieces, so this is going to be a 45-degree angle that we'll work with. What we want to find is that distance from the mound to first base, and we know that all the bases are 55 feet apart. So we can use this oblique triangle that we just formed to find x. We don't know a ratio, a side and the angle opposite it, so we need to use our law of cosines again. So that side that we're looking for, squared in this triangle, is equal to the other two sides squared minus 2 times the product of those two sides times the cosine of that included angle, and it's 45 degrees. So again, we'll take the square root of both sides and use the positive value that we get. So x, or this distance from home plate to first base, is going to be approximately how many feet? If you run that through your calculator, you should get a distance of 38.91 feet. Okay, here we're going to use Heron's area of a triangle formula to find the area of a couple triangles when the only parts known are all three sides. The law of cosines can be used to establish Heron's area of a triangle formula. So let's just look at this triangle ABC. And side A measures 8, side B measures 12, and side C measures 10. What we need to find is S. S is equal to 1/2 the perimeter, A plus B plus C, and side A was 8, side B is 12, and side C is 10. So this S value that we need is 1/2 30 or 15. So now we can plug that into Heron's area of a triangle formula, because we can find it by getting the square root of S, which is 15, times 15, take away one of the sides, times 15, take away a second side, times 15, take away the third side. And now I'm going to simplify that up a bit before I put it in my calculator. So I have 15 times 7 times 3 times 5 underneath that radical. So we've got the square root of what here? Looks like the square root of 1,575. And is that a perfect square? No. So I'm approximating this area to 2 decimal places. The area of this triangle is approximately 39.69 square units. Include with your notes of this video guided practice problems 1, 2, 4, and 5 on page 891 of your textbook.